Okay, so we are back on page 291, okay, and we're going to start the next unit. So you might want to grab some highlighters. There's lots of definitions in this section. We're going to be highlighting. Of course, if you just have a pen, you can underline it and maybe make yourself some notes later to help you remember what these definitions are, or maybe you remember some of them, so it's all good. Okay. So this is kind of a review of what you would have learned last year in 10C. I'm just going to try to, it seems blurry on my end. Okay, so function and function notation. So a function itself, okay, a functional relation or a function is a special type of relation in which each element of the domain is related to exactly one element of the range, okay? So each element of the domain has one element in the range, okay? If the element of the domain is related to more than one element, okay, then it's not a function, okay? So this, you will be tested on that, okay? Function notation. So function notation itself, so it's read f of x, so this example right here, so f and then brackets x, we would say f of x. So under a function f, the image of an element x in the domain is denoted by f of x, okay? Which then, like I said, it's read like that. So some of the examples we talked about, so if we ever have like an area example and say we get, I don't know, a polynomial, -3, just making things up here. If we get, okay, what is a if x is equal to 2, then we would say, we could word it like this. So technically this is a of x is equal to all that. So then a of 2, I would just substitute in like that and then solve. Okay? So consider a function f defined by the formula. So for example, 4x minus 8. Okay, we would write that as function notation, or it's called function notation rather, if it's in the form of f of x is equal to something. Or it could be g of x, or the example, ooh, trippy, or the a of x that I gave you this example for. Okay? Okay, so we can show that under the function, under the function f, the image of 5 is 12. Okay, so then we would write that as f of 5 is equal to 12. So then using this notation right here, okay, I'm going to just see, okay, it's back. I don't know if that froze for you, but I'm going to keep going. Okay, so we can show that the image is 5 of 12. Okay, so this is the equation right here. So then if I put in f of 5, it equals 12. Okay, so that's the function notation. If I wanted to write this as a graph, equation of the graph of the function, then I would put y is equal to that. Okay, so then in this case, if I'm looking at this, so that's, if you remember, y is equal to mx plus b. Okay, my slope would be 4, my y-intercept would be -8, so this is just a simple linear relationship. So then if I put that in right there, that means that my x is equal to 5, and my y is equal to 12, so then the coordinate point of 5, 12 will be found on this line. Okay? Alright, so we can also show that under the function, the image of 2 is 0. So same thing, we substitute the 2 in and solve, and we get 0. Okay, so because that's equal, so then same thing, that 2 is our x, that is going to be a point on our function or our graph or our equation. So then what we would say, okay, the 0 of the function, so whenever you've got function, okay, we're talking about zeros. If we're talking about equations, we call it the root, but guess what? It means the same darn thing. It's just a terminology thing. So if you have found the zeros of the function, you have found the roots of the equation. Okay? All right, zeros of a function. So a little bit more about this and an example. I'm just going to move this up a bit. Okay. So a zero of a function is a value of the independent variable that makes the value of the function equal to 0. Okay, so that's the definition of it. So we're going to highlight that. So it makes the function equal to 0, and they can be found by solving this equation. Okay, so f of x is equal to 0. So what that means is if f of x is equal to 7x minus 21, okay, if we're finding the zeros, we set f of x equal to 0. Just like that. Okay, so set equal to 0, and then solve for x. So then we're going to bip that 21 over to this side. Okay, and then we're going to divide by divide by 7. So then x is going to be equal to 3. Okay, so then we would write, okay, well, therefore, the zero of the function is 3. Okay, so on this page, we reviewed what a function is. Okay, we know that it is a function if it's got one domain to one range. If it's more than that, it's not a function. Okay, so if there's more than one element in the range, then the relation is not a function. We reviewed function notation, so f of x. We compared zeros of the functions to roots of the equation, and then we went ahead and actually solved for a 0. Okay, so let's see. We're going to do a bit of an investigation, and we are going to, I'm just going to move this up. Okay, we're going to connect the roots, x-intercepts, and zeros. Okay, we already know that roots and zeros are the same, and x-intercepts are too. So if you have found one of them, you found all of them. But we're just going to actually show that this is true. Okay, so we've got the graph shown here. Okay, so once again, linear equation. We've got a slope of 2, so that means you've got a rise over run is equal to 2. So every 2 you go up. So if I start here, 1, 2 go up, I go over 1. 1, 2, over 1, etc. Okay, and then that minus 6, that's my y-intercept. That's why my graph goes through -6, because my y-intercept is -6. Y-intercept is when x is equal to 0, and then vice versa. X-intercept is when y is equal to 0. Okay, so determine the x-intercept of the graph algebraically and graphically. Okay, well, graphically is pretty easy. Okay, the x-intercept is when y is equal to 0. Okay, y is equal to 0 right here. So there it is. Okay, so x is equal to 1, 2, 3. Okay, so that's the graphically part. To do it algebraically, this is where we set, because y is equal to 0 for the x-intercept, so then we take this equation, we set it equal to 0, and then we just solve. Okay, so you would move that 6 over, and we'd have 2x. Okay, and then you would divide both sides by 2, so therefore getting x is equal to 3, which that's what we got for our graph. And it's always a good verification to do both of them, because if you say you graphed it and you got an answer and you were checking your algebra and your graph, they were different, you'd want to make sure you either put this in correctly or solved correctly. Okay, so then determine the root of the equation. Okay, well, that's the same thing. Okay, this equation right here is just already set to 0 for us, so we just have to solve for x, and of course we get the same value, which is what this is. C is asking. State the connection between the two, between the x-intercepts of the graph and the roots of the equation. Highlight that different just because you know how I love to color code. Okay, so x-intercepts of the graph, roots of the equation. Okay, so I don't think we need this much space to put they're the same. I guess let's put the same value just to elongate it a tad. Okay, so consider the function f of x 2x minus 6. What is the 0 of the function? Okay, so roots of the equation, x-intercepts of the graph, 0 of the function. Okay, it's going to be 3. Okay, so you could go ahead and just say, okay, this function, the 0, f of x is equal to 0, and then so then you would show that. But of course, we've done this 3 times now. Okay, x is going to be, oopsies, is equal to 3. So the connection between the x-intercepts of the graph, so once again, just to kind of solidify this in your brains, x-intercepts of the graph, roots of the equation, and zeros of the function. Okay, they all be the same. Okay, same values. Oh, I don't know why I did that. I meant to write all. They're all x is equal to 3. Okay, so investigation 2. So this was a linear relationship. Now we've got a quadratic relationship. Okay, so we're going to see if this holds true for a quadratic. So Jacques is determining the roots of the equation. So roots of the equation, x squared minus x minus 6 is equal to 0. He wrote the equation in factored form, because of course this is just a trinomial here that we can factor, and used the zero product law to determine the roots of the equation. Complete his work and solve for x. Okay, well, let's just start by writing this down again. Okay, so then we would just need to factor it, because that's what Jacques did. So then x, and so then we think, okay, what multiplies to be negative 6? That adds to be negative 1. Okay, so 3 and 2, you're probably thinking. So 3 times 2 is 6. So then in order to get a negative 1 sum, our 3 is going to have to be negative. So then we would put negative 3 plus 2. And then remember, we set each one of these equal to 0. And then we can just take that shortcut, and it's going to be equal to the opposite. Okay, x is going to be equal to 3. X is going to be equal to negative 2, because we've set, just once again, we've set each of these equal to 0 and solved. Okay, so then those are the roots of the equation. Okay, so let's talk about the x-intercepts of the graph. Okay, so if you were to plug this into your graphing calculator, which you should all be able to do at this point, okay, this is the graph that you would get. Okay, so then the x-intercepts, once again, are going to happen when y is equal to 0. So that's going to be along this line. So those are our 2 x-intercepts at 1, 2, and 3. And then negative 1 and 2, negative 2. Okay, so we can just write x is equal to negative 2 and 3. And then state the connection between the x-intercepts of the graph. I'm like in highlighter heaven right now. And then roots of the equation. They're the same. Okay, I'm sure this is shocking to you. All right, now we're going to, explain the connection between the factors. Okay, so these are the factors. So the values of x, which make the factors 0, okay, are going to be the same as the roots of the equation. So if I were to put this 3 in, that would make that 0. If I were to put this negative 2 in, that would make this 0. Okay? So the values of x, oopsies, I'll try spelling it correctly, values of x, which make the factors 0, are the same as the roots of the equation. See, that's the roots of the equation. Okay. Okay. Give you a second there. Okay. So now we've, once again, x-intercepts of the graph are equal to the roots of the equation. So now we're going to revisit the zeros of the function. Okay, so consider the function g of x is equal to x squared minus x minus 6. So the zeros of the function, that means that g of x is equal to 0. Okay, and of course I'm factoring the same thing. Okay, so of course I'm going to get the same answer. Okay, so the zeros are 3 and negative 2. Okay, so state the connection between the x-intercepts of the graph. Okay, so x-intercepts of the graph of y is equal to x squared minus x minus 6. The roots of the equation, so notice the differences I'll just circle in red. So I've got y is equal to, this is set equal to 0, and this is a function. So the trinomial stays the same. It's just that the graph is going to be in terms of y is equal to something. The roots of the equation, okay, the equation is going to be equal to 0, and then the function is going to be listed as a function as either g of x or f of x or whatever. Okay, so all the same values. All right. Okay, so we're going to do a few class examples, but just to reiterate, okay, this right here, just remember that they all mean the same thing. It's just kind of a technicality of how is that, well, in this case, quadratic equation, but over here it was the linear equation. Okay, so whatever that equation is, how it's presented. Is it a graph, is it an equation, or is it a function? All right, so fill in the blanks, okay, in the following statement regarding the function with equation y is equal to f of x. So, sorry, this is, I'm trying to, every time I move it, it kind of goes out of focus. Okay, so what goes with function? That is the zeros of the function, okay. What goes with the graph? Those are the x-intercepts, okay, and then what goes with the equation? Those are the roots, okay, and of course they are all the same dang number. Okay, so then we've got the same graph, so this is the same example as before. Okay, so I know this seems a little repetitive. Okay, so graph is x-intercepts, and they're going to be the negative 2 and 3. Okay, the y-intercept, once again, the y-intercept is when x is equal to 0, and x is equal to 0 along here, so then we would just see that that's negative 6, which hopefully you see the connection there. The constant in your equation or graph or whatever it is going to be equal to your y-intercept. That's something that you should always remember. Okay, the function has the zeros of, once again, negative 2 and 3. And of course, the equation has the roots of negative 2 and 3. Okay? All right, so let's look at a different example. So class example 3, we've got a new equation. So remember, equations are set equal to 0. So describe how the 0 feature on the graphing calculator can be used to determine the roots of the equation. Okay, so if you were to just graph, so for example, y1 is equal to your equation, okay, then you would just have to, from here, determine the x-intercepts. Determine the x-intercepts of the graph using the 0 feature. Okay, and then of course the x-intercepts are going to be the roots. All right. So I want you to plug this into your calculator. So use a graphing calculator to determine the roots of the equation and sketch the graph on the grid provided. Okay, so using just the Inspire. Okay, oopsies. Let's move that up. So f of x is going to be equal to 2x squared. My fingers aren't working. There we go. Minus 7x plus 3. Okay, so I would press enter, and there's my graph. So this right here, I see. This is see how my axis is kind of wonky. So I would want to go into my windows, and maybe yours is set fine right now, but I'm going to put my window settings to this. So that's going to be an x min of -1. My x max is going to be 5, and auto's fine. And then y min we've got -3, and y max we've got +5. And then I'm going to press enter, and so now it's going to match my what I've got right here. So now, actually, do you know what? Let's go back to menu. Back to window 4. And so I said that it was okay at auto, but let's just put it as 0.5. So then each little dash is going to be 0.5. There, then we can read it better. So see right there, that's right at 0.5, and then that'd be 1, 1.5, 2.5, oh gosh, 1, 2, 3, sorry. Okay, so 1, 2, 3 is right there. So it's going through there, and it's going through the 0.5. Okay, and then reading up here, it looks like it's 1, 2, 3, 4, 5, 6, and each one of those is a half, right? So that's going through 3. 1, 2, 3. Okay, and then the bottom is actually off the graph, so I'm just going to quickly put my y min, I'm just going to put it at -5 just so I can see it better. There we go. And so if you wanted to find that lower point there, you just go into Analyze Graph. So now you, with the 82, 83, 84s, just help each other out how where we went to find the intersection, that's going to be where you do the zeros, okay, or the minimum. So the minimum, we're going to talk more about this in this unit, but if you did the minimum, that would allow you to find exactly where this minimum point is, okay, the lowest point. So zeros, though, we want, so I'm going to do zeros. Oh, and I hope this is just fell asleep. Wake up, computer. There we go. Okay. So I'm going to move it over here. So I'm going to click once on that side. Whoa. And once on this side, and sure enough, it gives me 0.5 and 0, which is, you know, what I figured it was, 0.5 and 0. And then you can do it again, so Analyze Graph, 0, and you just do the same on the other side. And then, yeah, sure enough, it is 3. You always want to check because, you know, maybe it's off by a bit, 3, 0. Okay, so then we can just go ahead and finish the sketch of our graph. I'll just show you quick how to find the minimum point, just in case. So you still go Analyze Graph, minimum, and then you do the exact same thing, left side, right side of the minimum point. Okay, and so then we see, not that it's that important for us, but it's at 1 3/4, and then it goes down at -3.13. So that just helps you really when you're sketching your graph. So I should actually have this down a bit, just so that I can be a little bit more accurate. It's if you can't be accurate, then just label. Another thing you can do if you go to your table, so 7, split screen, you can also get information off your table. So for example, this is your x, that's your y. Right here, I see that my x is 0 and my y is 3. That's my y-intercept there. Okay, so x, or no, I said that backwards. X-intercept, sorry about that, guys. It's because they're both equal there. If I were to go up 1, there's my 0 and 3. So x is at 0, and that's at 3. So that's my y-intercept, and those are my two x-intercepts. Okay, putting this away for a second. So determine, so we sketched it, we determined the roots. Use the x-intercept to factor the expression. Okay, so this is when it can help us out a little bit. Oopsies, there we go. So we know that the x's, okay, are going to be equal to 0.5 and 3. Actually, I could have written that up here. It's okay. So those are my x's. So that means that my factors, when I've got this all factored out, okay, is going to be -3, because remember, it's always the opposite sign. Okay, so those are going to be my factors, but remember I've got a 2 here. Okay, so I would need to put a 2 out front, because x times x is x squared, and then times that 2, that's when I've got that 2x squared. So then I can actually just distribute that in. So 2x, so 1/2 times 2 is just 1, x minus 3. So there's the factored expression. All right, there you go. Okay, so finding zeros of a function. So, oh, I need to move this up. So to find the zeros of the function, you can do two things. Okay, you either substitute 0 in for f of x and then find the roots, or you can graph it and determine the x-intercepts of the graph. Okay, it's always a good idea, if you're not sure about one, do them both and make sure that they are equal. Then you will be confident in your answer. Okay? So now finding the roots of the equation algebraically. So finding the roots of a single variable equation may involve factoring, which is why we've done all this practice with it. Okay? Except in the case of a linear equation, because that's, once again, linear equation y is equal to mx plus b, not going to require any factoring. You might have to pull out a common factor, so like if this was like y is equal to 2x plus 2, okay, well you could put like 2x plus 1, okay, but you're still, when you solve this, okay, x is still going to be equal to -1 in this case, okay? So anyway, so techniques for factoring, you can use common factors, difference of squares, trinomials in this form, trinomials in this form, and then perfect squares too. I don't know why that's not listed, but you could also do the perfect squares. Okay, so find the roots of the following equation. So this is equal to 33. We're going to scoot that over there, so minus 33 minus 33, so that it's equal to 0. Okay, then we're going to factor it. So x. So we're looking for something that multiplies to be 33 and adds to be 8, right? So that would be 3 times 11, I think would work. Yep, so then in order for this to be positive 8, so I'll just put that down there. In order for it to be positive 8, that means that 11 has to be the positive one. Okay, and so then when you set each of these equal to 0, okay, x is going to be equal to -11, and x is going to be equal to positive 3. So the roots are x is equal to -11 and 3. Okay, this one right here, it's actually already factored for us. Now this 6 doesn't carry a variable, so we don't really care about it. We do care about this. So, and this one's easy, x is equal to 3. This one, if you can't do the mental math, that's fine. You just have to take that extra step, set it equal to 0, scoot that 5 over, okay, then divide by 4. Okay, so then the roots are -5 over 4 and 3. Okay, and this one right here, I do see I have a common factor, so I'm going to take that 2 out. Okay, and hopefully this looks familiar to you. Okay, this is a difference of squares. So remember, when you've got a squared minus b squared, that's going to be equal to a plus b times a minus b. This'll keep coming up, so definitely difference squares, something to commit to memory. So then I keep the 2 there, and I go x plus 2, x minus 2. And so these two x's are just the square root of x squared. These two 2's are the square root of 4. Okay? So then once again, this is equal to 0. I don't care about the 2. I just care about these x values. So then x is going to be equal to negative 2. X is going to be equal to positive 2. So I can just say the roots are going to be plus or minus 2. Okay? Okay. So let's talk about zeros and y-intercepts. So for the following functions, find the zeros. Okay, so functions finding zeros, that means I'm setting my f of x, or it could be anything, here it's a g of x, equal to 0. Okay. And then I just rewrite out all those equations. Okay, so this one right here, I do see that there's a 5 in common, so I'm going to factor out a 5, x squared plus 3x minus 4. Then I'm going to, oops, helps if you can see, split my brackets there. I know that's going to be x and x, so I'm thinking what multiplies to be 4 but adds to be 3? Okay, so that would be 4 and 1, because 4 times 1 is 4. 4 minus 1 is 3. Okay, so then from there, once again, don't care about that 5. Negative 4, positive 1. So the zeros are negative 4 and 1. Or I could just say x is equal to negative 4 and 1. Okay. Finding the y-intercept. So remember I said that the y-intercept is going to be the constant. Okay, so y-intercept is going to be equal to negative 20 there. Okay? So I'll give you 3 minutes, or no, I'm going to give you 2 minutes, to factor this one out on your own. Okay, and you can go ahead, if you're getting ahead, you can try this one too. I want you to get the y-intercept find the zeros and the y-intercept. Okay, so I'm just going to put 2 minutes on, let it run, and then I'll come back to you. Okay, there's the 2 minutes up. So for B right here, we can do this as the AC, so just kind of as an aside. So what multiplies to be AC that adds to be B? So 3 times 10 is 30, and then B is negative 11. Okay, so hopefully you got negative 6 and negative 5. Negative 6x subtract 5x is going to be negative 11. So then we would write this out. So we put our, just like we did last unit, we put that term first and the constant term last, and then we just arrange these. So I'm going to put the 6 with the 3 and the 5x at the back, and then I do the common factor. So this is factoring with grouping, if you forgot. Okay, so then I'm going to factor out 3x, and then I'm going to get x minus 2, and then here I'm going to use a 5, x minus 2, and then of course I put these two together, 3x plus 5, x minus 2. Okay, so that's all factored out. So then this is going to be x is equal to negative 5 over 3, right, because you would solve for that. So x is going to be equal to negative 5 over 3, and then this is going to give me a solution of 2. Okay? And then the last thing I have to do is my y-intercept, which, because I ran out of room at the bottom here, I'm just going to identify, actually I'll do it on that one too, that those are my two y-intercepts. Okay? Alright, so for this one here, it's already factored out for us. So this is going to give us an x equal to 0. This is going to give us an x equal to, so we would put that 1 on the other side, and then divide by 2, which would give us negative 1/2. So the zeros are going to be x is equal to 0 and negative 1/2. And the y-intercept, this one's not as obvious here, and because we've got this being multiplied in, like if there's no multiplication, you literally just take the constant term. Okay, but in this case, the y-intercept, I think it's easier. If you could graph it and you could find it off there, okay, or you could just, the y-intercept is, of course, when x is equal to 0. So you can always substitute in, okay, so g of 0 is going to be 2 times 0, 2 times 0 plus 1. Okay, well, that's going to be 0. 0 plus 1 is just 1, but 0 times 1 is 0. Okay, so that means that the y-intercept is 0. So a lot of people will say, oh, it's 1, because they see that constant there, but we're actually multiplying it by something, so then you would want to do it this way. All right? Okay, so hopefully there was no main problems there. Help each other out, of course. Okay, and the last example. So for each of the following functions, use a graphing calculator. So make sure you've got your graphing calculators out. And we are going to do 3 things. We're going to sketch the graph of the function, so get it on our graphing calculator and then just copy it into here. We're going to find the zeros as exact values. Okay, so that usually means we want to do it algebraically. Okay, and then write the function in factored form. And yeah, so let's start off here. So 3x squared plus 4x minus 7. So let's grab our calculator. So you do this too, because of course everybody's got different calculators. Not everybody, you know what I mean. Okay. 3x squared. Okay. Yep. Okay, so I'm definitely going to have to adjust my windows. So a lot of times, most of the time if you do zoom fit, it'll work okay. Let's see if it works for me. Nope, sure didn't. So then I'm just going to go ahead and adjust my windows. Standard puts you at a 10 by 10. Oh wow, the lights just went out in my room. I'm still here. There we go. Okay. So that gets us a little bit closer, and our y-intercepts there, our x-intercepts are there, so that's not bad, but we know we have to go down a little bit more, so let's go for settings, and I'm just going to go down to -10. Let's see if that does it. There we go. It's all on there. So then when I draw this out, I'm going to want to make sure that my scale, so since I'm 10 by 10 by 10, I guess this one goes up to 6, but whatever. Okay. So there's my -10, and it looks like I'm at, so 10, 8, looks like it's at an 8. And then 1, and then it goes 1, and it's between -2 and 3. 1, 2, so it's somewhere there. It's definitely there, and then it's there. So this is maybe not going to be the most beautiful graph, but just do your best. And that's where labeling comes in handy. Okay, so that's 1, 2, 3, 4, 5, -1, -2, -3, -4, -5, and then actually we're good for there. Okay, so graph is sketched. So then the zeros of the function as exact values. So I think analyze graph. Just wanna. So this one we're pretty sure it's 1, but we're just gonna double check. Yep, it is 1. So x is equal to 1. And then on this side, 6, analyze graph, 0, 1, what is it? Oops, went too far. 2.33. Okay, well 2.33 is 2 and 1/3. Okay, 2 and 1/3 is 7/3, and then it's negative. Okay, so you could also go to your table if you wanted to, and you do split screen table, and you can read it down. However, you do have to go into you can go into settings somehow. I'll show you that later. You can go into settings and you can, you can set the table to have fractions, but for now, just use your brain. Okay, so then that right there is the exact values. Now we need to write the function in factored form. So we know that, so this is 1, 2, 3, factored form. So my f of x is up here, okay? So, I mean, you could use this to help you, or you could just do it the normal way, like 3 times -7 is -21. So what multiplies to be 21 and adds to be 4? Okay, well it's going to be 7 and 3, and then in order for that to be not negative and that to be positive, our 3 would have to be negative, right? Yeah. So then from there, just a minute, I want to make sure I did that right. Oh, what? Yeah, -21 adds to be 4. So then that's going to be x minus x plus, oh yeah, because of that 3. Oh yeah, I'm sorry. Okay, it's getting late. So 3x squared, and then that's what I would do my grouping with. So I would put that -3x there, and then the 7x, and then I would put that 7 at the end, and so those are, I would group those 3 together, so you've got 3x, and then you've got x minus 1, and then here we would take out a 7, x minus 1, then I'd put those 2 together, so 3x plus 7, x minus 1, there's my 7/3, my -7/3, and there's my +1. Okay, so then in factored form, I would just leave it like this. Okay. All right, so we've got the 3 answers there, 1, 2, and 3. And then for part B, the only difference is now we would call this a cubic relationship or cubic function because it's got a cube there, go figure. Okay, so when you graph this, okay, you should get roughly this. Okay, so you will get your y-intercept. You will get 3 x-intercepts. Okay, so plug this into your calculator. Make sure that you can read all of those off. Okay, and so on your calculator, you should get zeros of -1, 1, and it's going to be 7, is it 7 quarters? Yep, 7 quarters. Okay. So then for graphing it, and once again, you could do this first. You could factor this out. We haven't done too much factoring with cubic, so actually it would be easier to do this. So once you've got these here, okay, you know that it would have to be x plus 1, x minus 1, x minus 7 quarters. Now, that's a 4 there, so there's going to be a 4 involved. Okay, so in order to make sure that you did this correctly, leave that into your graphing calculator as your, say, y1, and then substitute in for y2, so you go down, all this in, and you should just have one graph, and so that one graph means that, yeah, these two are actually equal. Okay, so yeah. I was about to ask if there was any questions. Obviously, I would not be able to hear you. So that's the lesson. If you have any questions, just come see me Monday after school, because of course Monday at lunch I have staff meeting. And yeah, have a great weekend, and see you later.